much more familiar thing for all of you. Okay, let's start. So here we are going to now discuss the issues or the questions or things related to the magnetics and the elements of the circuit and all these things. So how do we compute certain quantities? How do we ensure that we have the capability to generate torque and all these things in the motor? So simple question, let us say, without going much into details of other things. If I have a simple core, it is closed, no air gap in there, and I have a coil which is carrying current I and having number of turns N. The cross-sectional area of this core is AC. So this cross-sectional area is AC, and any other thing if you want to consider, that is there. Now the task is, let us say if I want to compute the flux generated in the core, so how do I compute? This is the question. It may be a simple, very elementary question for all of you.
Flux density into area.
Yeah, when question comes, how do I compute flux density?
MMF by reluctance.
Good. So new term has come up, which is basically MMF. So here, let me define MMF for some of you, just for a revision sake. So this is basically defined like this. Now, what else is there? MMF by
Reluctance.
Okay, so another term has come, reluctance. Now, we don't know as of now what reluctance is. Okay, I don't give a straightforward definition or expression for that. Now, how do you say this is correct? Why do you say this expression is correct? What's the motivation behind that? Okay, in other words, if I draw a coil like this, having just one turn and current I. Now, if I ask that what is the flux at within this boundary of this coil, or let's say in the vicinity of the coil, is this expression correct now?
No, sir.
Okay. Let me have a wire, piece of wire which is carrying current I, and I ask for magnetic field at some point P. Is this expression correct now? You understand the question, right? Is this expression valid for these cases? Why?
No, sir.
Sir,
The question is why?
Sir, this one we are using circuit analysis, sir. KVL, KCL are not valid everywhere. So
KVL, KCL are not valid everywhere.
like
this.
No, sir. In circuit theory they are valid, but if we consider field theory,
so this also would be some circuit, right? Ultimately, let's say a bigger loop. I make a loop like this. So we are trying to separate out the field theory and the circuit theory and these things, right? So, I mean, just I'm curious that from where these expressions are coming out. How are you deriving? How are you getting these expressions?
Similar to electrical circuit, how we are writing B equal to R into I. So here, if we transform that to magnetic circuit, that current is equal to flux, and that voltage equal to MMF.
The question is, that is all analogy.
yes, sir.
But how do you know it is that?
Sir, like they are just like if we compare circuit theory and field theory, like if we see the solutions, we can, if we are able to get approximate solutions, like we can say, like through some certain assumptions, if we are getting approximate solutions to certain degree, whether we use both the theories, we'll get the same answer.
Correct. So somewhere, now if I ask that, what is universally applicable to all these situations? Do you have one solution which is universally applicable to all?
Time varying.
Yeah.
So time varying through.
No, I am not talking about time varying or invariant, all these things, but I am talking one, let's say, set of equations or set of some theory which is applicable to all these situations.
Sir, electromagnetic equations. Right.
Yeah, what do you call it?
Yes, sir.
Isn't it? This is applicable to all the situations, whether it is circuit or field or anything.
Yes, sir.
Now what this is? What is Maxwell equation? What are these equations? So basically these are relating the four quantities. Let's say electric field density, electric field intensity, magnetic field density, and magnetic field intensity. These four quantities, it is relating through different equations. These are interrelated. Now, whether the system is time varying or time invariable and all these things, that's a different issue. But this equation connects all the possibilities for these four quantities. And of course, through the material property and all these things are also included. Now, what are these equations? So basically these equations are, say, either you have a closed surface integral of electric field intensity. So electric field density. So what is the response of this, or what is the output of this?
Charge enclosed.
Huh? So whatever charge is enclosed divided by epsilon naught.
Epsilon.
Because this is density only. So on the other hand, if we have closed surface integral of magnetic field density, what do we get?
Zero.
Zero.
Zero. Because we always have magnetic dipoles, no? We don't have a monopole. The magnetic dipoles always exist. And here we may have isolated charge. So that is how we are arriving to these equations. Now, other way or other two equations could be, if instead of going for a surface, closed surface, you go for only closed contour and you try to do the same thing. Now what is this?
Something like time rate of change of flux density, something like.
Yes.
Yes.
This relates to, because this is nothing but your EMF when you are integrating. Of course, closed loop should go to zero, so this will also get confined and something will come. So this is how it is relating to the rate of change of flux over here. And similarly, if you have the integration of magnetic field intensity over a closed contour, what do you get over here?
I enclosed.
Is that all?
And
There is-
displacement current then.
Yes.
Yes, yes.
Another very important component which is coming on account of the displacement current, or something which is related to capacitor when we have the time varying magnetic field and electric field. So these are the four fundamental equations which are basically governing all the rules and equations whatever we are able to see in our electromagnetic theory. Now, which of these equations are applicable and what are the scenarios under which we can approximate these things or how to solve these equations? This is what basically gives you the solution of, let's say, flux or energy or any other thing which you want to compute in this system. Now, when we are talking about, say, scenario where we have a core with, let's say, coil over it, and we have just a simple core, magnetic core, it's there, and n turns are there, and current I is flowing. So first thing what we need to have is that what we are trying to solve. So we are trying to solve for the flux. Now, when we are saying this is magnetic core, that means the permeability mu is something which is much more greater than the permeability of air. So our first assumption that if we want to solve this, first assumption what we need to take to solve these equations for this system is that the field lines or magnetic field lines are basically confined within this core. Which means the field lines which are going out of the core, some leakage or fringing, whatever you want to call, these are very, very negligible compared to what is there within the core. So almost all the field lines are confined within this. That's the first assumption, and that is what we mean by saying that our permeability is much more higher compared to the air. Basically, mu is nothing but mu r times of mu 0, where mu r is much more greater than 1. So something like 1000, 2000, 3000 and so on. So that's a big number. The other assumption we will have when we want to solve is that the cross-sectional area for this core is basically uniform throughout. This cross-sectional area, say AC, is uniform. It's not changing everywhere. So that's another assumption if you want to solve this. And then we need to consider some mean length. Mean length meaning, let's say if you go towards the very inner edge of this core, you have the least length if you move around this core. And if you take the outer edge, you have the largest length on this core. So we are taking the average of both. So considering the mean value of core length. So with these three things, what we are saying that, okay, now if we try to solve these equations for this particular system, we can get information about what is the flux and what other properties are. So for example, if you take this mean length, which is drawn in this thick line, so say this length is LC. Now what we have basically, when we are putting this fourth equation over here, and this is for the closed contour, and these integrations are over the surface. So I should mention S, open surface integrations. Now, when I'm putting this, there are two things coming over here, I enclosed plus the displacement current what we have just now discussed. So for normal circuit scenarios, what we say, magnetic circuit scenarios, that our frequency is normal, like it's not very high where the interwinding capacitance starts coming into picture. So which means that we are ignoring this displacement current. We are not considering this part. So this again simplifies our system. Now what we have, I enclosed. So if we move around in this path, what we will find that the total amount of current enclosed in this path is basically the current which is flowing multiplied by the number of turns. That is what we are encountering in this. So this H into mean length LC is basically N times of I. This is the first thing what we are getting. The other part what we know is basically our magnetic field density and magnetic field intensity. These are related for any material in this form. So we can take simple magnitude as well, need not consider the multi-dimensional vector or something. Simple magnitude will also work over here. Now we want to compute the flux or the flux density. So we can just insert over here whatever we have found here. So mu times of Ni by L. And we know that our core area is uniform. So flux is nothing but flux density into the core area. Correct? So what we are finding here, that if you multiply AC on both the sides, your flux is coming out to be something which is related to this form. Now this is what the component which is coming over here, Ni, this we have defined as F, the MMF. And this part which is coming over here is something what is defined as reluctance. Something similar to resistance which is offered by electrical circuit. Reluctance is the property which kind of resists the development of flux in the circuit. So this is inverse of that basically. This is 1 by R, what is written over here, mu A by L. So this can also be called as permeance. The inverse of reluctance is permeance. What is the similar definition for the conductance? So now we have the equation what we were looking for, where reluctance is defined as L by mu times of AC. So we understand if the core length is too much, of course, this is going to have more resistance. If the permeability is too high, then this means the reluctance is going to be lower. If core area is too high, reluctance is further going to be lower. So that is how these are related. Now, this is what we have computed, right? Understanding my point?
Yes, sir.
Okay.
Yes, sir.
So these definitions are now clear, that why we are using and when can we use that, when can we not use. So let's say for any random shape of core, you cannot use that unless at least few conditions are satisfied. We cannot say that, okay, we have just a coil and we can compute is using this equation. No, that's not valid. This is our general understanding also. This cannot be valid. Now, what if there are, say, the core is given and I have a small slot opened over here in the core, some air gap. Say this length of this air gap is Lg. Now again I have similar scenario, the current I flowing into it, the number of turns are N, and then we have the magnetic material with permeability mu. So now again I'm trying to compute the same thing, flux in the core. So from here what we have understood that we can make an analogy with the electrical circuit. Electrical circuit analogy says that you have a circuit where you define the in a lumped manner the total reluctance at one place, the MMF as the voltage source, and flux as the current. So because all these conditions are satisfied here as well, so we can make this similar circuit. But now we have two different materials coming in this path. One is air and one is this magnetic material. So what we can do, we can split the reluctance for these two paths. We can take this black line what I have drawn, that path, the reluctance of this path as say R1, and the reluctance of this blue line as R2. So these two reluctances are now coming in series. And we know what these values are. So R1, from again this expression we can compute. What is R1? So basically LC divided by mu C times of AC. And R2 is nothing but Lg divided by mu 0 times of Ag. And we also say that, okay, for uniform cross section, AC is nearly equal to Ag. There is no problem in that. Now, once we have this understanding, what basically we are doing that, okay, my MMF is nothing but Ni. So my flux, which is coming in this system, is basically Ni by this R1 plus R2, the total reluctance. This is easy. There is no problem in that, right? Fine. Okay. Now, let us go one step further. Let's have simple coil and try to relate its electrical properties with this whatever magnetic flux and these things we are able to generate. So which means if we are applying, let's say, voltage V, how is the electrical circuit going to be defined in terms of that? So what do we have basically? We have, because we have the coil over here, we are applying some voltage, so there will be some flux. And because say that the flux is varying, it cannot be a DC voltage applied across the coil. So we have some AC voltage applied over here, so flux is also varying. So because of this, we will have some EMF induced across this coil. Understanding my point? That's the simple understanding. Again, we are trying to correlate with the Maxwell equations which we have written earlier. So now we are trying to have this third equation. So let's ignore the resistance for simplicity. What we have basically is that EMF will be nothing but the total flux. Now because there are n number of turns and the flux is phi, so something which is known as flux linkage, that means the total flux associated with the coil, that will come into picture. So this is what we will have. Correct? So see, I mean, it doesn't matter whether it is air core or magnetic core, doesn't matter. Just a coil is there and you are applying some voltage V and we are trying to compute the elements of this circuit. Now what we have basically, we have the voltage applied for this, and this is coming like over here, and lambda we have computed n times of phi. Now we know that what is phi? Phi is basically mmf by R. So mmf again we can write in terms of the number of turns and the current flowing in the coil. Then we have reluctance. Reluctance is basically again the similar definition we have, L divided by mu A. And this is true for even a coil which is having air core or this kind of, but the length should be more. It cannot be just one turn. So these assumptions we need to have. Now this inductance or the flux linkage what we are writing, we can basically divide it into two parts. One which is only associated with the circuit and other part which is related to the excitation. The current is our excitation which is going into the coil, whereas the other part, this is only the circuit or the system property, number of turns and the permeability of material, area, length. This is all only related to the how you have organized your magnetic circuit, nothing to do with what you are feeding in the system. This is what is basically defined as the inductance. Because we have just one coil, so can be called as self-inductance. So that is what we see when you write the KVL. This comes in the form of d lambda by dt, and because lambda has two components L and I, so it can be expanded like L di by dt plus I dl by dt. Understanding my point? Now what we have basically is that once we have got the voltage, we can always compute the power V into I, and then we can always go on compute the energy associated with that. All these things can be computed on basis of these equations. Now a general question, let us say when we talked about talked about the iron core, where we had some kind of air gap given, some slot was cut. Now here, is it valid for any length of slot what we are cutting over here, or is there any restriction on that as well? Is there any restriction on what is the length of LG should be? Yes. Of course, it cannot be too large, right?
Sir, fringing effect doesn't come into picture.
Yes.
Then okay.
So how do we quantify that? Fringing effect, of course, we want to have minimum because we want to have these circuits accurate as much as possible. But how do you ensure? So the definition or general understanding says that this length should be much less than the square root of the area of this cross section. That's the general understanding. So what happens, let us say we have the slot cut open for our core over here. The fringing effect what we have heard. So basically the flux lines are flowing from one part of the core to other part of the core. Similar to we may have in the electrical machines also, we have a stator and rotor where one part is stationary, another is moving. So of course, air gap is required. Now, that air gap length when we are deciding, we need to ensure that it should not be too large that the flux lines start jumping through air. No, through a different path other than this, what is going in the same axis. So to avoid, and this phenomena, what I'm writing over here is called fringing effect. So the flux lines are not going in the same axis, but these are deviating from the main path. That's what is called fringing. And we must avoid that to have no good approximation and good computation. Of course, we are losing some things over here, some capability of the motor. So that should not happen. So this is the condition which we must ensure to avoid fringing. Understand my point? Correct?
Yes, sir.
Okay. Now for the same core, let us say we are given an iron core which is having some slot cut open. We have some magnetic flux density over there, magnetic field intensity over there. So general question, if I ask that, how do you feel the energy? It's inductor, right? Kind of inductor, having a coil and then core. That's what it is essentially. Now, how do you think the energy is distributed in this core? Is it uniformly distributed or more in the iron core? How is it? What's your general feeling?
More in the air gap.
Okay, that's good. How many of you agree with this? You all agree with that or not? You need to speak. I need to understand that how much you are already aware about all these things. So Tejdeep is suggesting that more energy will be stored in this. So what is energy? Basically, we are talking about half Li square, right? That's what we are talking about. Correct? So he is suggesting that more energy would be stored in the air gap. You all agree with that? There are no marks for this question. You can answer freely. You agree or not?
No, sir. It's if air gap is more, then the inductance is lower.
No, that's okay. See, for this system, let's say there is some energy U associated with this system. Now, what I'm trying to understand, where this energy is going to be stored in the, is it uniformly stored in the system? Or it is confined somewhere else more and somewhere lesser?
More in the aircraft.
Yeah, Ajay?
More in the aircraft.
Why do you say that? Right? This is what we need to have. No, the general understanding should be there about this. So let us say when we are talking about energy, so there is basically when we have any system, say some magnetic field density is there, some magnetic field intensity is there. What is the energy density for any system which is having these two things given? Half B into H, right?
Yes, sir.
Correct? Now, what we have total energy, let's say there are two parts, say the iron part and the air gap part, Ui and Ug. So, we will certainly have the iron part energy as BiHi times of Vi. Vi is the volume of the iron part. And similarly, for the air part, we will have BgHg and Vg, right? Correct?
Yes, sir.
Yes, sir. Yes.
Now, because we are talking about same structure and the area is more or less uniform, the air gap length Lg is maintained within this constraint, so the flux density is more or less going to be same. You agree with that?
Yes, sir.
You agree with that?
Yes.
Yes, sir.
Correct.
Yes, sir.
Now we have Hi, Vi plus Hg and Vg. So again, now B equals mu H is applicable everywhere. But when we are saying B is constant, which means what? This mu and H are basically managing this constant flux density among themselves, which means if mu is high, H has to be lower. If mu is lesser, H has to be high to maintain the same flux density, right? The meaning is that when we are talking about iron part, again the flux density is B, so Hi and this B are related like this, B divided by mu C, the permeability of the iron, and for air this will be written like mu 0. Now if you take out B again and expand the Vi and Vg part also, you can simply write Vi as Ai into Li and Vg as Ag into Lg. So Ai and Ag are almost same, say taken as area A. These two are different. So we will have B square A coming out and Li by mu C plus Lg by mu 0. Again, mu C we can write in terms of mu R times of mu 0. So this also comes out. And what we will be remaining with is that Li by mu R plus Lg. So this is the proportion of energy which is distributed in the two parts. You see this proportion, this is common factor. Now mu R is something which is changing of the order of say 1000 to 4000 it could be. So this is going to be a small number compared to Lg, which is why we say that you can even ignore this part compared to the Lg section. So which is why the energy stored in the coil is very much close to what is stored in the air gap. So when we are making DC inductors, what we do basically, we provide a small air gap so that the number of turns required are not too high for achieving the same inductance. The reason is that the energy what we are trying to store in core, much bigger portion of that can be stored in a small air gap. So for DC inductors, we try to have some small gap so that the number of turns requirement comes down heavily for achieving the same inductance value. You understand my point?
Yes, sir.
Fine?
Yes, sir.
Okay. Now let's have two coils in the system on the same magnetic circuit or the same core. Say this is having current I1 and number of turns N1. This is having current I2 and number of turns N2. Now what I'm trying to compute over here is, see, similar to what we have done for single coil, V is nothing but d lambda by dt, right? So here we will have basically two flux linkages, lambda 1 and lambda 2. Now what I'm trying to compute is the circuit property, which means what is the self-inductance of these coils, say L11, L22, and what is the mutual inductance, L21 or L12. So how to compute that? Again, similar thing we have to follow what we have done so far. Try to have the total MMF. What is total MMF? N1 I1 plus N2 I2. This is the total MMF in the circuit. And in response to that MMF, this circuit will generate a common flux, which is basically F by R. Reluctance, because it's a uniform core, so we can simply write L by mu A without any problem. Now, this flux what we are having can be written as N1 I1, N2 I2 divided by L times of mu A. This is the flux flowing into the coil, in the magnetic core. Now, each coil will have flux linkage according to its number of turns. So, for example, the coil 1 will have flux linkage N1 times of 5, whereas coil 2 will have N2 times of 5. Now, if you simply expand this part, what you will find, lambda 1 will turn out to be N1 square mu A by L times of I1 plus N1 N2 mu A by L times of I2. And lambda 2 will come out to be N1 N2 mu A by L times of I1 plus N2 square mu A by L times of I2. So this is where we get the information about the self and mutual inductances. What is self-inductance? That is coming because of the excitation within the coil itself. So this is something self-inductance for the first coil. You can call it L11. Similarly, we have L22. Sorry. Which is coming on account of the excitation in the same coil or the properties of the same coil. This is not dependent on the other coil. This is only the property of the same coil. Number of turns are only the what is having what we have for the particular coil. Now, the other term which is coming over here, this is called mutual inductance. L, say this is 1, 2 and this is 2, 1. Now this is coming on account of the kind of, you can say, the influence of both the coils. This is another circuit element we have got, which is coming on account of both the coils as a combined effect. Clear? So when you are writing voltage equation for 1, you will write this plus, yeah, I mean lambda 1 itself will contain information about both the things, and V2 will have this. And then you can expand lambda 1 and lambda 2 and you can write the complete equation. Fine?
Yes, sir.
Yes, sir.
It's only
Yes.
basics I am going through, because next we are going to discuss machines and little bit of magnetics related to different machines. So just I am revising all the basic concepts. Fine, there is no issue in this. Now let's have some discussion about the magnetic material. So far what we have assumed that our magnetic material is kind of linearly behaving, and it's behaving in a linear manner, and there is no deformity, you can say, in terms of the magnetic circuit element. Let's say if we talk about inductance, this is uniform inductance, that's what we have assumed so far, or the permeability mu, that's uniform permeability for the system or for the magnetic core. But is it always true? The question is that. So this is where we go for something which is relating these two fundamental quantities in the system, the magnetic flux density and magnetic field intensity. Or in other words, we say that the cause and effect in terms of this flux linkage and excitation. These are basically same equations, only written at either microscopic level, that means at particular element you can write and then this will be true, whereas this is something related to macroscopic, which means at the circuit level. So if you expand this, you will reach back to B equals mu h. So for example, lambda can be written as n phi and L can be written as again n square mu a by L times of I, and again this can be written as this. So if you just shuffle all these things, what you will find that you are reaching to. So Ni by L is basically your H. So these two are same equation. So whenever I'm talking about, let's say, this BH graph or the BH curve, that is also relating to the excitation and the flux linkage. So something common which we all know very well, that we have any material is having its own property, and that is given by the BH curve. So what do we know? Let's say if I talk about air. So for air, basically this mu0 is a constant number. Okay, what's the value of mu0 for air?
4 pi into 10 to the
4
minus
pi into
7.
10 to the minus 7.
That's a small number, right?
Yes.
So which means what? Yeah. So which means what? If you keep your excitation, let's say I on the x-axis, or in other words H on the x-axis, and your flux linkage on the y-axis, or the flux density in other words on the y-axis, what we will find that as you increase the excitation in any coil which is having air core, so you will find that certain flux density you are able to generate, but this will be a very small number. Understanding my point? So for generating some substantial amount of flux density or flux linkage, you need to apply large amount of excitation. But this curve is very much linear, which means there is no limit how much flux density you can achieve. Only problem is you will have to have large excitation provided for the system to achieve that flux density. Whereas if we talk about any other magnetic material where we have mu, which is coming as mu r times of mu o or mu 0, this mu r is pretty large, 1000, 2000, 4000, something like that, then this curve basically becomes much steeper. Something like this, which means what? To achieve the same flux density what we were doing earlier, we need very small excitation, and we can achieve that. But the problem is that there is certain limit how much flux density can be achieved for any core. So what happens if you keep on increasing the excitation? Your flux density will increase linearly up to certain time, and then it will start saturating. So this curve will start bending and it will go and saturate to certain value. Now beyond this, if you apply any amount of excitation, it's not going to cause much difference in the flux density. You understand my point? This we all know very well, right?
Yes.
Correct. Now, if this is magnetic material, what we can do, we can try to come back. No, the excitation we can try to reduce, but instead of following the same curve, this will follow a different path and it will come and meet the y-axis at some other location, not at 0. This is what we know as the remnant magnetic field. Remnant magnetic field meaning the value of magnetic field intensity of this density in the core at 0 excitation. Now, if let's say for some reason we trying to have 0 flux density in the core from this point, then we need to apply some negative flux intensity or some negative excitation. So the point where it meets the x-axis again, that means 0 flux density, this point is called coercive field density, HC. Forcefully we are bringing down this to 0, the coercive magnetic field density. And if you continue going in the other direction, what you will find that this again goes and saturates on the other side. And again try to come back, it will come and meet at some negative remnant magnetic field density. And further continues, so again there will be one more coercive field intensity, and then it will continue and meet the saturation point again. So this is what is called as the magnetic hysteresis curve. So hysteresis meaning that it is having the memory of the previous excitation, nothing much, like a capacitor. So it has the voltage. If you have already charged it to some value, it may retain that value for certain time. So which is same for this magnetic material also. If you have excited to some field density, it may retain that value for certain time. Sometimes this is required. Let us say when we are trying to make magnets, we need to have this kind of material which can retain the property. So you excite the magnetic material to saturation and then you remove the excitation. So what will happen? The remaining portion will be the remnant magnetic field in the material, and then it can act as magnet, which means without any excitation it has certain magnetic field density. Correct? Now sometimes we have DC motors also. There also we need some materials which can retain, let's say self-excited motors. We need to have some retention of magnetic field if we want to start from zero, right? So sometimes these kind of materials are used for DC motors as well. These materials are classified as hard materials, hard magnetic materials, where the remnant magnetic field is there and they have large coercive field intensity, which means they need large negative excitation to remove that magnetic field. These are called hard magnetic materials. So basically HC is large for such materials. Now, if there is something called hard magnetic material, there must be something called a soft magnetic material, because for example, if you talk about AC motors, we don't need to have remnant magnetic field too much. We need to overcome that quickly as possible, because we are going for sinusoidal excitation, AC excitation. So it has to come down to zero quickly, which means the requirement for HC should be low. So it will get excited quickly, let's say like this, and may have some remnant magnetic field, but this will quickly drop to zero, and then a thin BH curve will be formed over here. These are called soft materials, which are needed for say AC motors and so on, where you don't want any intentional this remnant magnetic field or something. So that's the classification for the materials. Now, only thing we need to keep in mind that when we are moving for this saturation, towards the saturation, what is happening? The value of mu r is changing.
Yes.
It is reducing and going close to 1. And the effect of that is the inductance of the system is also changing. In fact, it is reducing. So when we operate very close to this, this axis, let's say almost linear zone, then we can expect a constant inductance or constant mu. If you try to saturate it, go beyond this knee point, you expect that this is going to change. Correct? Is that fine?
Yes, sir.
Okay.
Yes, sir.
So what we will do tomorrow, we will discuss the BH curve for the magnets and how these are expected to be, what is the important property that we need to have, and which of the magnets can be considered as good magnets for our machine. And then we will slowly move towards the reluctance motor. Fine. So I know this is just a revision, but still if you have any questions, you may ask.